Good afternoon, Dr. Laha. So I think who all are going to help you with this demonstration today right now?
Good afternoon, all. Nishant will be
Yeah,
helping
so
in
I,
actual
I would like
experiment.
to request Nishant to introduce himself right to the audience. Nishant, can you kind of switch on your video and yeah, so that audience should know you.
Yeah, so in camera, actually, Anvesa is helping. So Anvesa,
So, am
Yeah,
I
so can
audible now?
you put the camera in the landscape mode because that would ensure that. Yeah. So we tried that in while doing the PLD. Can you do it in landscape mode? Okay,
Yes, landscape.
so is there a possibility of doing 100% in this camera because you have various options in which you can check the camera. So then what happens is this entire screen would be visible. Otherwise, only a small section is visible. Currently, the feed from the camera is occupying only a very small section of the screen.
okay, then we'll whenever required, we'll move the camera actually with the stand. Then
Okay. Okay, and I can also see there's a lot of echo.
that it will not come.
It will not come. Yeah. Okay, so
So,
Nishant, maybe we can start then in that case. Yeah,
uh,
thank you.
good afternoon, sir, and good afternoon, everyone. Myself, Nishant, and I'm PhD scholar, Department of Physics, IIT Patna. So, today, mainly I'll explain atomic force microscope and a little bit about scanning tunneling microscope. Mainly, these two instruments come under
So Nishant, for a moment,
the category of
I
probe
would like to
microscope.
stop
In
you.
probe microscope is divided into two parts, AFM and SPM. AFM
Dr.
is stand
Ranjit
for atomic
and
force
Nishant.
microscope, and SPM stand for scanning tunneling microscope. First of all, I'm going to discuss about atomic force
Yeah,
microscope,
Dr. Ranjit and
AFM. So
Nishant,
mainly in
just hold
AFM,
on for a
actually
moment.
one probe of one cantilever attached a probe at top of it, and a probe of size few nanometer, maybe diameter of the order of maybe 20-30 nanometer.
I want to
It
know from
touch the
participants
sample
if the
and
voice
to
is
do the
fine.
raster scanning.
Karuna, can you let me
Okay.
know if the
And
voice is
it
fine?
experience the force, mainly Leonard Jones force, whatever force,
Is also coming, sir.
and it records.
Hello,
So this
Hello?
is
Karuna, the voice is good.
this
Yes, sir.
is
Voice is coming, sir.
Voice is good.
schematic
Okay, okay,
and
please go ahead.
AFM. This is your cantilever, and at the top of it there is a tip, and to observe the up and down of the tip, there is a laser incident at top of tip and reflects back, and there's a detector. And detector detects the changing the position of the cantilever. So the nature of force is this. Suppose this is the sample, and this is the tip. So distance between r, and if tip goes closer to the sample, then it is in attractive zone, and suddenly it comes into means highly attractive region, and again if we reduce the separation between tip and the sample, the force increases, and this increase in repulsive zone. So this is mainly the working of AFM. So there are mainly uh, two AFM has been categorized in two parts. One is static AFM, another is dynamic AFM. AFM, static, and dynamic. Again, static AFM it is also called contact AFM, contact mode AFM, and dynamic mode is divided into two parts. One is intermittent contact mode, contact or this is also called tapping mode. And second is non-contact mode. This non-contact mode is also called frequency modulation. And this tapping mode is also called amplitude modulation. I will tell you later what is amplitude modulation and what is frequency modulation. So mainly when initially when AFM was made, then it was limited to mainly very very smooth samples, and which are and it was not useful for soft materials. It was not useful for soft materials. So dynamic mode come into picture. So what is exactly static mode and what is dynamic mode? Suppose this is your sample, and this you have to scan, and this is my cantilever, and there's a tip of, just imagine this is the tip. Okay, so I'm scanning this, and this process is called raster scanning, and the photodiode detector just observe its change in position, and this cantilever is attached to a piezoelectric material. Piezoelectrical such materials, when we apply field, then stress can be generated, and vice versa is also true. If we if we apply stress, then charge may be generated. So this cantilever is attached on a piezoelectric material, and which is can do this raster scanning, and its position, the position of the cantilever is observed by laser. So suppose we have very sharp tip and we are scanning soft material like polymers, DNA, or proteins, in that case, or some biological cells, and if we scan it using sharp probe, then it may damage the soft material. Suppose we are scanning very hard material, okay, then in that case this probe may be damaged. So in order to scan such kind of material, there's another kind of mode was introduced, that was called dynamic mode. In dynamic mode, cantilever actually oscillates. Just observe my finger. This is the cantilever. It oscillates at a fixed frequency and do the raster scanning like this. So in this way, it cannot damage the soft material. So in dynamic mode, there are two types. Amplitude modulation, and frequency modulation. Mainly, most of the time amplitude modulation is used. Okay, so what happens in amplitude modulation? In amplitude modulation, the cantilever is oscillated at its fundamental resonant frequency, and while scanning, it come across some material. Suppose while scanning, our cantilever face this height. So in that case, suppose it is oscillating like this. So just encountered this height, the amplitude will change a little bit, and in order to keep the constant amplitude, the cantilever will go a little bit up. Okay, so this process is called amplitude modulation, and this is also called tapping mode, AC mode, as well as intermittent contact mode. Okay, in frequency modulation, the same thing is done used with frequency. It is oscillated at the fixed amplitude, but frequency changes due to interaction, and the feedback circuit try to keep constant the frequency. Okay, so here we are going to scan a sample which is gold coated mica, and we will do contact mode imaging first. This is our AFM. Its model is multi-mode 8, broker multi-mode 8. It is already in contact. So it just take a scan कर देते हैं. Just okay. Yes. So, this intensity of work.
I think I can show here, right?
Yes. So we can observe here. This is our cantilever, and yes, this is the cantilever, and laser is falling at the top of the cantilever, and after reflecting back, it is going towards the photo detector. The dimension of length of the cantilever is typically varies maybe 100 to 200 micron, maybe more or little bit less, and width of the cantilever maybe 10 to 20 micron, thickness maybe 2 to 3 micron, and at top of it there is a tip what we cannot see using a optical microscope. And it's pointing in means yes, and towards the sample. This is from upper side. This view is from upper side.
So is it possible to little more focus or this much only?
No, it is focused on the sample actually.
No, you can focus on the
Okay.
little better. You can tell that. Yeah.
This is the tip.
Yes.
You can tell that.
So mainly cantilevers are made up of two materials, silicon and silicon nitride. So silicon nitrides are normally for soft kind of cantilevers. Suppose we have to scan soft materials in contact mode, then in that case we use silicon nitride. Normally we use silicon, and this is this is a conducting cantilever made up of silicon, and it is platinum coated. So here we will take IV also. Current mapping while touching the samples, we can at the same time we can take the current mapping also. So now we are going to scan it. So now we will approach this and we will start scanning. So meanwhile, I'm going to tell about how photo detector works actually. It detects the position. So it is 4-quadrant photo detector. There are 4 parts of it, mainly A, B, C, D. When we start scanning, then we try to focus the laser beam at the center of this photodiode. Okay. So while scanning, cantilever moves up and down. So laser sports, according to that, laser sport goes up and down. So how much up it is and how much down it is, in order to know that, we merely define a quantity which is called deflection, which is equal to intensity in A plus intensity in B minus C plus D. To normalize it, we add all the intensity, A plus B plus C plus D. So suppose cantilever moves up, then laser spot will move up also, and the intensity in A plus B will be greater compared to C in C plus D. So in that case, the deflection will be positive. Deflection signal will be positive. And suppose our cantilever moves down, so in that case, the total intensity in C plus D will be greater than A plus B. So in that case, this quantity will be negative. Okay. So in this way, it detects how much cantilever is moving, how much up or down. Similarly, when we do contact mode imaging, it goes left and right also. So in that case, we define another quantity which is called friction, which is equal to friction. Friction basically detects how much it is going left and right. It's moving left and right. So in that case, P plus D minus A plus C upon A plus B plus C plus D. Suppose our tip bend a little bit and laser sports move right in this region B and D. So in that case, the quantity B plus D will be greater than A plus C. Okay, so this quantity will be positive. Friction will be positive. And if cantilever bends in left direction and the laser spot will also go in left, so the intensity in A plus V will be greater than B plus D. In that case, this quantity will be negative.
Yes, Nishant, any difficulties?
Yes, sir. So actually, sir, we have started scanning.
Okay. You're showing
Ah.
them.
Okay. See, there are some parameters here. When we start scanning, the first thing is scan size. Here we have put scan size 500 nanometer into 500 nanometer, and aspect ratio means it is square, so aspect ratio is 1, means length upon width. X offset, Y offset. This is, suppose maximum we can scan 20 by 20 micron here, and suppose we want to scan a area in the corner. So in that case, similar to the coordinate, we can shift our position of the cantilever by putting x offset and y offset. A scan angle. A scan angle. Suppose we are scanning in this way. The cantilever is scanning this way. So we want to change the angle. Suppose in this way we want to scan. So by changing angle, it changes the angle of scan, means angle of scanning. And this is sample line, means how much line it will scan in a single image. So here we have put 512 into 512. And these are the gains, integral gain and proportional gain. Basically, these are the crucial parameter in AFM. Basically, it optimize how much a cantilever is sensitive. Means our piezo is how much sensitive. Suppose we are scanning something. This is a sample. This is cantilever, and it is scanning like this. Okay. So if the gain, integral and proportional gain, both are too low, in that case, it may hit this height, and it will not go up. So in that case, its response is quite slow. And if we increase the gain, feedback gain, too high, in that case, it will catch, means random noise. So we have to optimize these two quantities, basically gains. Okay. So, and here, since we are this image is basically topography in contact mode. This is deflection error, and this third one is basically current mapping we are doing, but we are not getting good image. Means with the scanning, our cantilever is means also mapping the current. Current sensitivity.
100 kg, 100 kg.
Maximum.
नहीं होता है. So this is all about the contact mode. Now we want to open our system little bit, and we want to show the system, and we will change the module, and we will put tapping mode, and we will show the scanning. Okay.
This resolution,
Achha,
completed.
So some of the images I'd like to show. See, this is gold coated mica, and this is 3D picture. Basically, the main advantage with AFM, we can get X, Y, and Z. So here, this is a 3D view of our image. Some other images I would like to show. This is a seat. So here we can see its 3D. We can observe its 3D view. So we can find here step height also. Yes. So here we can measure. It is 50 minus 100, minus 100 to 50,
150.
150. Its thickness is around 150 nanometer. Here we can observe. So main advantage with atomic force microscope, along with X and Y, we can measure Z also. While suppose our sample is conducting, in that case, we can put conducting cantilever, we can touch and we can take IV of, suppose we have quantum dot, maybe DNA or any sample of a nanoscale of uh, dimension. We can put, we can scan, we can observe at which place our content dot is. We can place our cantilever there and we can press it and we can take the IV. So similar IV has been taken here. We can observe. See, this is a non-linear IV. It has been taken of means a single layer of discotic liquid crystal. Okay. Now we are going to change our module and we will show the tapping mode. So I'm withdrawing the sample. So this is nothing but camera. This upper head, this is camera, and to so this is our scanner head, and this is cantilever holder or tip holder. Is it?
Right side you are showing camera there.
No, sir. So this is probe holder. Here, this is the chip, and cantilever is attached to it. Whenever we try to change the modes, we have to change this one. This is scanner head, and laser is inside this one, and we would like to open it also. I will show the piezo. Actually, here in our system, basically sample moves. Sample is at the piezo. This is our scanner, and this is our sample. So this is our scanner head. When we put the cantilever inside it, this is laser. You can observe here, and we focus it, and detector is in this side, and this is our sample holder here, and sample is itself at the scanner, and scanner is this is piezo. Piezo. This is the sample. It's gold coated mica. It is at the conducting base, and we put this base here, and this is the our piezoelectric scanner. When we start scanning, basically this oscillate. It moves up and down, and at the same time it do the raster scanning also. Instead of cantilever, our base moves in our in our design. Means Bruker multimode 8. So now we are going to change the module for the same sample. Since previously we saw the contact mode, so there in contact mode, cantilever does not oscillate, but when we do the tapping mode or intermittent contact mode, the cantilever should oscillate. So we will, because of that, we have to change this probe holder, and here this is the probe, means this is a chip at the top of it is the means probe is there, and it is attached with a shaker piezo. Shaker piezo, the piezo which keep oscillating the cantilever. Okay, so mainly this is the main difference between these two types of scanner heads. Just after changing the scanner head, our first task is to incident the laser at the top of the cantilever. So mainly to change the position of the laser, we move these two knobs to change the position of laser. Yeah. So in this screen display, we can observe three things: vertical, horizontal, and sum. Sum is the total intensity uh, of the laser at photo detector, which is around 5.1 here. And vertical is nothing but the deflection quantity A plus B minus C plus D upon A plus B plus C plus D. I told you just some time before. And this horizontal is nothing but the friction quantity. So before starting this scanning, we have to keep some maximum, and vertical and horizontal should be close to 0. So we have aligned the laser. We are going to align the photo detector now. Yes. So we can observe here the vertical quantity is 0.09, and horizontal is minus 0.03. So it is close to, both quantities are close to 0. That means our laser spot is at the center. Now we will uh, uh, bring our cantilever close to the sample mechanically, and after some time, when we observe that our naked eye cannot detect the distance between cantilever and the sample, then we do the automatic approach and it is done by the software engage. Okay, sorry. We will change mode here. We'll put tapping mode, tapping in air, soft tapping, load the experiment. So experiment has been loaded. Now our first task to find out the fundamental resonance frequency of the cantilever. So how the electronics does it? There's a Saker piezo. We give the range, maybe from 100 to 200, from 50 to 300, like this. And in this range, means from 100 to 200 or 400 to 400 kilohertz range, our Saker piezo try to oscillates the cantilever, and it finds at which at which frequency the amplitude of the cantilever is maximum. That amplitude, that resonant that frequency is the resonant frequency. So here we do auto tune here. Auto tune. So we can do manual tuning as well as auto tuning. So we are doing auto tuning. It will automatically detect the resonant frequency. So resonant frequency of our cantilever here is around 107.448 or 449 around. Okay, so now we will exit, and in our experiment we will oscillate our cantilever at this resonant frequency. So now we are doing auto approach, because if we will do it, will move the cantilever closer to the sample, it may hit. So now it is done by, it will take maybe 2 to 3 minutes.
How does it know it is not going to hit?
Okay. So what it does exactly, suppose this is our sample, and this is our cantilever. Okay, and our cantilever is attached to a piezoelectric material. So suppose initially distance r is very large, so it experiences the force, it goes a little bit and experience the force. If it experiences no force, it again goes down. Suppose it goes close to the sample and it hits a little bit. In that case, there is a deflect. It will absorb a little deflection. The cantilever will be like this. Okay, like this. So that deflection absorbed in the laser, sorry, photo detector, and on the basis of that, it stops there. Means feedback circuit says to stop at that point. In this way, it does the auto approach. Okay. So while it is approaching, I will explain it's little bit about its image analysis. Actually, it is approaching, so we can't do anything here right now. So, hello. So, if anyone, while it is approaching, if anyone has any doubt, then please ask.
Yeah, I request the participants if you have any question.
Nishant,
Please go ahead. So in the meantime, I would just like to also inform you that today happens to be the last day of our FDP. Tomorrow, notionally, we will meet in the evening for about half an hour or so, just to discuss future possibilities. If there are people who would like to use some of these facilities, how they can access it. So um, some of you have already started talking to people over here or contacting some of the people whom you have seen over last couple of days as coordinators or scientific officers or GTSS. So we'd like to formally do that discussion tomorrow. For today, we have lined up a very interesting pair of lectures. So one is by the head of the Chemical and Biochemical Engineering Department at IIT Patna. So he's going to talk about um, some of the work related to how technology can help in sustainable development. Like, so that is one talk. There's another talk by uh, Aideen R&D. So he himself is a very, very active researcher, and he's going to talk about um, like some of the work in the direction of sustainable development in his lab, like core technologies which are developed. So among them, he already holds patents for several of these developments. Um, like as far as I recall, there is one work which is very fascinating, which is related to large scale fabrication of graphene. There's another work which is related to how one really makes the surfaces of the plates of jet engines safe from any kind of frosting. So a lot of technological nanotechnology goes over there. So very interesting pieces of work he would be talking about. So I urge you to, of course, this is like stretching a little bit, but I'm sure you will benefit and not regret attending these talks. Thank you so much. Yeah. So Nishant, you can continue if there are no questions.
Okay, sir. So if I'll have more time, then I'll explain a little bit about SPM also. And meanwhile, it is getting approached. So I will show this the STM head. This is the STM scanner head, and we put STM probe here at this point. Uh, Here, this is STM probe. STM probe. Here. This is STM probe, and okay, this is STM probe, and it is mainly made up of platinum or platinum iridium. And STM works mainly on the basis of on mainly quantum tunneling. So here it doesn't experience the force. Instead of that, it measures the tunneling current between conducting sample and the tip, and the distance between the sample and the tip is of the order of 1 nanometer, around 1 nanometer, maybe less. And we here mainly observe the current in the range of nanoampere. So the main limitation of STM is it requires the conducting substrate, because it is observe the tunneling current, and if we have insulating substrate, we will not observe any current. So this is the main limitation, but the advantage of it, its resolution is quite high, and at ambient condition also it can give atomic resolution of highly conducting substrate. Maybe for HOPG, we can get within 1 hour atomic resolution, but this thing is not possible for AFM at ambient condition. So the main limitation of STM is it requires the conducting substrate. And for this machine, we have two scanners. One is large, one is smaller. Large scanners range is maximum around 20 by 20 micron, and small scanner. This is our scanner. This is large scanner. Its range is around 20 by 20 micron, and the range of small scanner is 100 by 100, 500 by 500 nanometer maximum. But small scanner is used mainly for high resolution imaging. This is small scanner, and we can easily get atomic resolution using STM. So we are not getting good image right now here in tapping mode, but we are trying to optimize here. This basically, while tapping mode, we mainly get three kinds of data. One is topography, means height. Another is amplitude. Another is phase. While oscillating the cantilever, whenever it encounters any height, suppose it is scanning and it encounters this height, so at that time it reduced its amplitude here, and in order to there's a change in amplitude here, and in order to keep the amplitude constant, it goes up, and that change of amplitude is plotted here in this second this image. This is height, this is amplitude, and this is phase. And corresponding to change in amplitude, there is a change in phase is also observed, and that phase is plotted here in this one. Okay, so in some cases, phase image is very high. One means amplitude and this height or topography. These two image are same, but phase image sometimes give good contrast between two different kind of materials. Maybe suppose we have two types of uh, polymers of different modulus, and if their height are same, their heights are same, then then both will be observed in amplitude and height. Their feature will be same, but in phase that might be difference. So sometimes phase image is helpful. Okay. Okay. Mhm. So okay. So in our machine, there apart from tapping mode, contact mode, there are other modes also. Another one is called CAFM, which is means current mapping, current spectroscopy. CAFM means we can take the current mapping, and current spectroscopy means suppose we found here one dot here, and we try to place our cantilever here, and after pressing we want to get IV here. Means it's means it's conductivity or something. So in that case, we put the cantilever here and we take the IV. So that is called current voltage spectroscopy. So that we can do here also. Apart from that, we can do capacitance mapping also. So means while making mainly semiconductor devices of out of microns or nanometer, it is required to map the capacitance, which actually tells about the performance of the device. So for that, capacitance measurement is required. So that we can do here also. Apart from that, we can also do MFM here, Kelvin probe microscope here, and we have EC cell also. EC cell in fluid. This is a setup for it. This is basically holder, and we can put our fluid here, and we can do the EC cell experiment here. Yes. And apart from these things, we have extra module also. This is the electronics. Basically, this is the signal access module. We can access all the signals coming from hardware to the controller, and we can feed here external signals. Maybe we can put wave function generator here, maybe extra lock in here, and according to our customization, we can customize this. According to our requirement, we will customize this machine. And apart from that, we have extra lock-in, and we have gigahertz range oscilloscope, and we normally used to connect parameter analyzer to this, and AFM tip works like a probe station, and we do the electrical characterization of nanoscale features. So
Thank you, Nishant. Yeah, I think a few minutes I'll just take. Anusha, can you switch off the video? No, it's still coming. Okay, so Nishant has nicely explained the whole setup that we have. The setup name is a scanning probe microscope. Okay, so that is the basic difference behind scanning probe, as well as what we started with atomic force microscope. So atomic force microscope is just one mode of the whole facility, whereas the other modes as he has already told, STM, then EFM, MFM, magnetic force microscopy. There are many different imaging techniques. More or less all of them do on the sample surface to find different kinds of properties. Other than imaging, as he has already told, you can do IV also, electrical current and voltage characteristics of your sample in its basic state, or even in a device. If a device has been made, you can do that also. 2 electrode, 3 electrode thing also can be done here. The only thing, you have to arrange properly the electrodes and give suitable bias voltage and all, and you can do the device characteristics also. Of course, there are advanced other instruments, particularly for device characterization, IV, for example, semiconductor parameter analyzer we have. Here also, to some extent, you can do that. And other than imaging and this IV, another important thing people do is the force versus distance spectroscopy. So it is just
Hello, no, sorry to bother
popularly
you, लेकिन title
those who
एक
work in the
title या
field, they
theme बता
popularly
देंगे?
called it as just FD curve. FD means force
Title
versus
या
distance.
theme बता
What
देंगे?
energy versus
हाँ
interatomic distance image
हाँ
in the
नहीं, आप
beginning
just
Nishant
verbally
showed.
बोल देंगे theme.
That is exactly what you can do the measurement also in the sample, and you can verify how it comes. Of course, there is a range. You cannot go at the center of the atom. So within certain distance, few nanometer up to few nanometer, you can easily approach your tip
I'm
and
sorry.
find out the force versus distance curve. That is also very important in some of the applications. People try to do that. So just to summarize, this facility is also accessible through like the other day I had given two addresses, site addresses. One is through our institute site, and then the other one is through iSTEM portal. iSTEM, just to recollect, I must say, Indian Science and Technology Engineering, this facility mapping, basically accessing all the facilities from anywhere in India. Okay, so that is iSTEM portal, and throughout this video, whatever demonstration was done, whatever facilities you could see, all those facilities are recently installed through support from Government of India DST FIST facility. So you can access them at any time or whenever you want through proper procedure. Okay, so I hope I think we can stop here. If Professor Thakur can allow, or others,
Yeah,
if
sure,
you have
sure,
any query,
sure.
maybe we'll be happy to
Dr. Ranjit,
clear if
I
something
really
is there.
apologize. I had to kind of catch up with one of the speakers in between and remind him about today's talk. Okay, so therefore my audio
Because
was
such a
on.
facility
So
covering in 1 hour, it's not always
yeah,
like possible. So we tried to give kind of information. Expertise will not come within this
yeah.
much. So
Dr. Ranjit, am I audible?
definitely we must have missed some parts that may appear very important to you or very basic to you. So you can ask, we'll clear it.
Yeah, Dr. Ranjit, am I audible to you? Hello? Hello, Dr. Ranjit, am I audible to you, or you have put on a headphone? Okay, can somebody else confirm?
Sir, you are audible,
Maybe.
sir.
Yeah, I'm audible, right?
It appears
So
there is
in
no
between, I'm
query.
really sorry that there was
Karuna
a
Kumari,
mild interference because of my end,
you want
at
to
my
ask
end.
something? You have something? Okay.
I think, are we going parallel? Ranjit, are we on same page? Yeah, okay. So see, any communication happens
Okay, so
only
far
if.
no question. So I think Professor Thakur may take over now.
Dr. Laha, any communication happens if both modes of both channels are open, speaking as well as listening. Yeah, so unfortunately, maybe my voice was not audible to you. I was trying to say something in between. Is it audible now? Maybe the arrangement in the AFM lab has been such that we are not able to hear, right, in between. Yeah, that's
Professor
okay.
Thakur, if you're
That's
saying
okay.
something, I think it's your mic may be
It's
off.
not audible. Yeah, I agree. That is the
see
reason
your,
why that is happening. It's very
profile
much
pic
possible in
getting
AFM
highlighted,
lab.
but nothing is audible.
Yeah, as others are able to listen, let's just
Okay.
wrap up here.
Now I could, yes.
Yes, Dr. Ranjit, you have to make sure that both modes are on, right? listening and speaking.
Yeah.
most
Sorry,
likely
it
your
was
speaker.
at my end.
Yeah.
It was not.
Yeah.
Okay.
Okay, so in between there was some interference from my end because I had to manage, or I had to kind of get in touch with the next speaker. I will again urge, there are two talks starting 5:15. So make sure that you are here by 5:15. Okay, you are back at 5:15. So from 5:15, there would be two 1-hour talks, roughly 1 hour with some follow-up discussions. So yeah, so please join. Thank you. I would look forward to everyone joining, as well as there would also be a kind of some kind of an evaluation session. So some questionnaire would be circulated. So I hope that like you would be able to solve them easily. So those would be based on whatever discussions we had over past few days. If people feel during the session that they need more time, they can let me know, and then I can extend the time of the quiz. So maybe it could be made till tomorrow morning or something like that. So that people can fill at leisure. So, however, as of now, as far as learning goes, please make sure that 5:15 everyone joins. Thank you so much. Yeah, I can understand everyone is so busy teaching courses, their own courses, but for this one day, I would urge all of you to find out a time. Thank you. Thank you so much. So now maybe like we can close this session temporarily. At 5:15, we'll start again.
Thank you all.
Thank you, Nishant. Thank you, Ranjit. Thank you, Anvesha. I think Anvesha is also there, right?